Modern climate models provide the best estimates for how the planet's climate system will respond to increasing levels of greenhouse gases in the atmosphere over the coming decades, and they are essential tools for resilience planning. However, based on abundant misinformation in various media, many people are under the false impression that climate models are flawed and unrealistic. In this module, we're going to review some aspects of climate models and have a closer look at how well climate models have performed when compared to observed climate. Anytime we attempt to look into the future, we're confronted with uncertainty, and projections of future climate change are no exception. In recent decades, climate scientists have developed increasingly sophisticated climate models for assessing future climate change. The uncertainties with the climate models are well documented, and although uncertainties do exist, the models have done a pretty good job of replicating observed climate change on various timescales. However, one does not need to look very far in the media to find statements that claim climate models are deeply flawed and should not be used to inform the planning process. For example, on November 28, 2017, Canada's former Minister of Finance and Minister of Natural Resources stated in a column in the Financial Post, and I quote, "Although you will not see this much in the media, climate model projections have turned out to be exaggerated, if not spectacularly wrong." This is of concern because this message reaches a broad audience when published in the Financial Post, and as a former member of the Stephen Harper cabinet, Joe Oliver's opinions are respected by many. So we're going to have a closer look at how well climate models actually have performed. It is likely that the world's first climate model was published in 1896 by Svante Arrhenius, who was a Nobel Prize-winning Swedish scientist and one of the founders of the science of physical chemistry. Without the aid of supercomputers and using only fundamental physical and chemical principles and a pencil, Arrhenius projected that a doubling of CO2 concentrations in the atmosphere would lead to a warming of about 4 degrees Celsius. This is definitely in the ballpark of projections of modern climate models that are run on supercomputers. Arrhenius also projected that the warming from increasing greenhouse gases would be amplified in the Arctic. Modern climate models have come a long way since 1896 and include many more complexities than in Arrhenius' early projections, but they still include the same basic understanding of how greenhouse gases will influence global temperature. This graphic illustrates the huge number of variables that go into a model of atmospheric circulation. Each of the thousands of three-dimensional grid cells can be represented by mathematical equations that describe the materials in it and the way energy moves through it. The advanced equations are based on the fundamental laws of physics, fluid motion, and chemistry. To run a model, scientists set the initial conditions, for instance setting variables to represent the amount of greenhouse gases in the atmosphere, and have powerful computers solve the equations in each cell. Results from each grid cell are passed to neighboring cells, and the equations are solved again. Repeating the process through many time steps represents the passage of time. The result is that climate models are now capable of producing very detailed and high-resolution simulation of Earth system processes. Right now we're looking at the ocean circulation in the Caribbean and northwestern Atlantic, and the Gulf Stream shows up rather nicely. Now we're shifting to a view of the eastern Pacific and can see a transition from an El Niño state towards La Niña conditions. These are all very detailed simulations, but the important question is how well do they simulate reality, and we'll explore that next. On the right-hand panel, we're looking at the observed pattern of global temperature as it changes through the seasons. You can see the broad band of warmth shift north during June, July, and August, and south during December, January, and February. In addition, you can see that the continental areas warm and cool more than the adjacent oceans. The left-hand panel is output from a climate model, and it is clear that the model does a good job of simulating the observed patterns of seasonal change in temperature. In addition to capturing the seasonal patterns of temperature globally, climate models also do a good job of simulating the patterns of atmospheric circulation. The right-hand panel is a composite of satellite imagery that shows observed patterns of atmospheric circulation. The left-hand panel is simulated water vapor and precipitation, and the similarity between the two is striking. The counterclockwise rotation of northern hemisphere storms, the clockwise rotation of southern hemisphere storms, and the westward drift of equatorial convective storms are all captured by the model simulation. The similarities between the observed and modeled is remarkable because none of these patterns are coded into the climate model. They all emerge as a consequence of getting the basic thermodynamic properties of the atmosphere right. It is useful to look at how well the climate models simulate observed changes in mean annual temperature. During the interval between 1998 and 2012, the models, shown in black, overestimated the change in temperature, shown in red. However, it is possible to find other intervals of similar length that show the opposite. Between 1984 and 1998, the climate models underestimated the observed change in temperature. This demonstrates that climate models are not great at simulating short-term variability. In contrast, when looking at the changes over a longer time span between 1951 and 2012, the match between modeled and observed temperature is very close. Enough time has passed now to be able to evaluate some of the projections of climate change that were based on the early computer climate models. In 1975, Wally Broecker published a paper in Science that suggested the world would enter a period of rapid global warming induced by increasing concentrations of CO2 in the atmosphere. Broecker's projection raised a lot of eyebrows at the time because very little change in mean global temperature had been observed in the preceding 2 decades. The graph shows the observed change in mean global temperature from 1900 to 1975 in blue, and Broecker's projection of global temperatures to 2010 in orange. It turns out that Broecker's 1975 model projections are pretty good. Broecker had no way of knowing with accuracy the rate of future greenhouse gas emissions, and, when adjusted to reflect the observed emissions, shown in red, Broecker's projections were spot on. The U.S. Global Change Research Program recently published a climate science special report in which they summarized the performance of the current ensemble of CMIP-5 climate models. The thick orange curve is the CMIP-5 grand ensemble mean across 36 models, while the outer dashed lines depict absolute ranges across all individual simulations of the 36 models. The observed time series of mean global temperature are shown in green, red, and black. The bottom line here is that the climate models have not turned out to be exaggerated or spectacularly wrong, but have done a good job of simulating mean global temperature change over the last 100 years. In 2014, the US National Academy of Science and the UK Royal Society jointly published an overview of climate science in which they state, detailed analyses have shown that the warming since 1900 is mainly a result of the increased concentrations of CO2 and other greenhouse gases. Continued emissions of these gases will cause further climate change, including substantial increases of global average surface temperature and important changes in regional climate. This perspective is shared by all major scientific organizations around the world and reflects the confidence that the scientific community has with the projections of the current ensemble of climate models. This wraps up the climate change module for climate change in Alberta.